Thank you.
Good. So the last speaker of the morning is Jonas Britz from Amsterdam. And he's going to speak about semidefinite hierarchies for diagonal unitary invariant quantum states. The floor is yours.
Thank you very much. And thanks to the organizers for giving me the opportunity to speak here. So in essence, I want to give an overview of our results from the first year of the PhD in the TENORS network. So this is joint work with my supervisor, Monique Laurent. And in essence, I'm going to speak about using semi-definite programming for a very specific class of quantum states, those so-called diagonal unitary invariant states. Okay, so let's jump right in. So let's define the basic objects of study. So we are going to be interested in bipartite quantum states. So every quantum system comes associated with an Hilbert space, which in our case is just going to be C to the n always. And then a quantum state is a Hermitian PSD matrix acting on this Hilbert space. And then if you have a composite quantum system, that means you have two different Hilbert spaces and you tensor them together. So our bipartite quantum states are acting on C to the n tensor C to the n, and we want them to be Hermitian and PSD. Okay, and then we need a notion of what separability is. So in essence, you take two vectors, x and y, from C to the n. You build the rank mon matrices, xx star, yy star, and you tensor them together. And we allow for all conic combinations of those elements, and this is what we call the separable cone. So a bipartite quantum state is separable if it lies in the separable cone, and if it's outside of this cone, we call it entangled. Okay, so anyone who's crossed paths with quantum information theory before knows that entanglement is a crucial resource, or maybe even the crucial resource in quantum information theory. But conversely to its importance, it's quite hard to test whether a given quantum state, whether a given bipartite quantum state actually lies in the separable cone. The problem is NP hard. Okay, so there are some methods for testing membership. And the key idea of this project was to suppose you have some extra structure on your quantum state. And then you can pose the question, okay, maybe I can implement these known methods more efficiently, exploiting the structure we have assumed initially. So in essence, we are going to need two ingredients. So the one thing is the DPS hierarchy. So this is an approximation of the separable cone relying on semi-definite programming. And then the other thing is the extra structure we are assuming, which is this invariance under diagonal unitaries. So those two things, DPS and CLDUI, I'm going to define more closely in the upcoming slides. And the goal of this talk is to make this sentence make sense to everyone in the audience by the end, which is that the sparsity pattern of CLDUI states is transferable to DPS certificates. So in essence, what this is saying is if you know that your quantum state is CLDUI, then you can implement the DPS hierarchy using semi-definite programming more efficiently. Okay, so this is going to be the plan. So let's start with the DPS hierarchy. Okay, so the DPS hierarchy works on the principle of state extension. So let's just assume we have a separable state, which is as simple as possible. It's just of the form xx star tensor yy star. Okay, so we have our bipartite state. And then we just extend whatever happens in the second register t times. So the notation is such that, okay, the rho AB means we have an A part, we have an B part. So the A part acts on the first copy of C to the n. The B part acts on the second copy of C to the n. And whatever happens in the B part, we just tensor t times. So we take this yy star and we tensor it an additional t minus 1 times to the state. And this is what we call the extended state. Okay, so this extended state satisfies several properties. Let's just go through them shortly. So people who are familiar with the partial trace will see immediately that tracing out the superfluous information we just added on just gives us back our initial quantum state. So for people who are not familiar with the partial trace, this is in essence a linear map where you eliminate the additional systems we just added. Then the second condition is, so similarly to the partial trace, there is the partial transposition. If we take the partial transposition of this extended state in the first S registers, so this notation means we are taking the transposition in the first S registers of the B system, then this is precisely what happens. The Y star gets flapped to the rank 1 matrix corresponding to the complex conjugate of Y. And as one can clearly see, this remains PSD for all S's ranging from 0 to T. And then the third condition is, which looks the most heavy, but actually is maybe the simplest one of the three. This is just saying that in the T registers we just added, our extended state is symmetric. So if you think of rho ABT as a hypermatrix, and then you have your T plus 1 row indices, and you have your T plus 1 column indices, and you can, for example, permute the T plus the T column indices corresponding to the B system without changing our extended state. Okay, so these three properties are in fact crucial to define the DPS hierarchy. So the DPS hierarchy now is defined as follows. We have a level T, which is an integer, and we collect all the states rho AB for such an extended state exists, satisfying those three properties. And there's a common point of confusion when I try to explain the DPS hierarchy, so maybe I try to catch it immediately. What we did here was we took something which is separable, and then we formed the extended state out of that. But of course, our rho AB doesn't need to be separable. It can be any bipartite quantum state, and you're just asking, does such a bigger state exist satisfying these properties? For separable states, you have an algorithm for how to construct these. But okay. And the cool thing is, so this is in particular the result of the paper by Doherty, Perillo, and Spedalieri. So this is also why it's called the DPS hierarchy, which basically says that this is an outer approximation of the separable cone. So this first inclusion here, I just argued, take something which is separable, then you can always do this construction here. So we get this inclusion. And this inclusion is also not so hard to see. I mean, in essence, if you have a extended state with T plus 1 B registers, you can just trace out one of the B registers and you get a certificate for membership in DPST. And then the crucial thing is that this approximation, in a sense, is exact. If you take the union, if you take the intersection of all these DPS cones, you get the separable cone out. So, yes.
Maybe I will contribute to the confusion. But the second constraint is non-convex in X, right? But you take the convex element.
Sorry, I did not understand the question.
I suppose that 1, 2, 3 defines a convex set in the space of rho AB states. Does it?
Yes, the DPS T are convex.
But is it?
Yeah, these are convex cones. Yeah.
Yes, and number 2 is non-convex. X is a no, linear continuation, like this partial transpose is defined on all tensors, right? It's like an operation that you can do on all tensors, not just on product tensors. The tensors takes
okay.
partial transposition.
Okay, so
it's
you
just a linear operation.
convexify that. You
So you basically say that like a linear operation, every tensor is PSD, so this is why it's a spectral.
Okay.
Okay. Okay. Any more questions to the DPS hierarchy? Okay, so this was the first ingredient we needed. I want to point out one more thing maybe. So suppose I give you a bipartite quantum state and you want to compute whether this actually lies in a specific level of the DPS hierarchy. Then you can implement these three conditions as a semi-definite program. Because the first condition and the third condition are linear. Yeah, you're asking whether a big matrix exists holding some linear conditions, and then the second one are a bunch of PSD conditions. So the DPS hierarchy is implementable as an SDP. Okay, so this was the first ingredient. Now we come to the second ingredient, which are the so-called CLDUI states. So what we have is we have the set of all unitary diagonal matrices. And the emphasis here really is on the diagonal. And then we call rho AB conjugate local diagonal unitary invariant, or CLDUI for short. If the following invariance property holds, you can hit your bipartite quantum state from both sides with U tensor U bar, where U ranges over all the diagonal unitaries. So it might be helpful to quickly pass this very long word. So the conjugate relates to the fact that in the B system we hit our quantum state with the conjugate. It's local in the sense that we are hitting rho with something separable, and diagonal is clear, unitary is clear, and yeah, invariant because this is an invariance property we are asking for. Okay, so this is the set of quantum states we are interested in, and there is several characterizations of this set. And one in particular is through the sparsity pattern. So a quantum state, or a bipartite quantum state, is in CLDUI if and only if its support is given by this very specific rule. So you can only have non-zero entries if your indices, either the both row indices are the same and both column indices are the same, or the first row and first column index are the same, and the second row and second column index are the same. And every other entry has to be 0. So I think I have a small picture here, or not picture, a small example. We're gonna see several of those. So this is the sparsity pattern for CLDUI in the case n equal to. So where the stars are, you can have whatever entry, and then you have all those zeros outside of the stars. And the third version to describe this set is through something which I learned a couple days ago, is called the, no, I didn't learn it apparently because I forgot the word again. Come again? Twirling. Okay, so this is the so-called twirling map. Thank you. So we've been using it without knowing that it's called that. Okay, so but how to think about this? So we look at it as a projector. It takes a bipartite quantum state and it projects down onto the CLDUI subspace. And in essence, what's happening here is we are forming a group average. So we are integrating entry-wise with regards to the Haar measure. And whatever comes out of this operation will then, since it is the group average, be invariant under this action on top here. And I also wanted to remark that actually you can restrict yourself to, so if you define the CLDUI set with this invariance property, you can actually restrict yourself to finitely many of those U. And then if you do that, then the corresponding group average would just be a finite sum. So maybe that's a little easier to deal with than the integration. Okay, so I think I have, okay, just to conclude that point, of course, then a state is CLDUI if and only if it's invariant under its projector. Okay, I think I have another example here. Okay, so this is the sparsity pattern for n equal 3. And as one can see, there are sort of two classes of entries. There is the diagonal, and then after permuting the rows and the columns, you get one additional matrix block. So we can encode, so this is the example for n equal 3, but this works in arbitrary dimension, where you encode your CLDUI quantum state into the sets of two n by n matrices. And this is also sort of why we got interested in looking at CLDUI states to begin with. Because, okay, so you have your state, rho LB, which is CLDUI, and then you can have a bijection with these matrices xy, which are not of the size n squared times n squared anymore, but n times n. And since they fully encode all the information of the initial state, then separability is also encoded on the level of the xy. And here the statement is that rho AB is separable if and only if xy is pairwise completely positive. And I don't plan on defining what pairwise completely positive means, but the interesting thing maybe is that it is a generalization of the completely positive cone. And it's a generalization in the sense that a matrix pair is pairwise completely positive if and only if x is completely positive. Sort of the diagonal elements are precisely the completely positive cone. Okay, so I'm speaking pretty slow, I think. So maybe I need to speed up a little bit, but okay. So far so good. We defined all the ingredients we need to begin with the new stuff. So we want to look at CLDUI states in the context of the DPS hierarchy. So somehow we want to define what it means to be CLDUI for such an extended state. And what one, yes.
Just a very short question. When you say completely positive, like there is like an optimization notion of completely positive, right? And there's a notion of a quantum channel being completely positive.
I mean the optimization notion. So the completely positive cone is the cone generated by non-negative x in Rn, and you look at x transpose. Okay, so what we want to have is a notion of being CLDUI on these extended states. And what we do is really sort of the obvious thing, because these extended states are symmetric in all the copies of the B register. What we do is we just, whatever happened in the initial setting, we just copy it t times. Okay, so I mean by not, we can define it like this, and then as on the previous slides, we get these equivalent characterizations. So the characterization through the sparsity pattern gets a little more convoluted because we get more indices for the rows and the columns. But in essence, you have a condition on the equality condition on the indices of the rows and the columns in case you are non-zero. And the equality on the right-hand side is an equality of multisets. And what one can actually do is if you set t equal to 1, then you have this equality of two multisets with two entries, and this precisely corresponds to the two cases we've seen for the case t equal 1. Okay, and then you can also define the projector again. You just tensor whatever happened in the B register t times. Okay, so these are all the ingredients to state the main result. Okay, so suppose you are given a CLDUI state, And you want to test whether it lies in DPST. So you're asking the question, does such an extended state exist satisfying the three properties of before? Then the statement is, if this is the case, then you can also project this extended state down to this new subspace without violating any of the three conditions. So in other words, you're given a CLDUI state and you want to test membership in DPST, then you can restrict yourself without loss of generality to extended states which already lie in CLDUIT. So this is the first statement. And then the second statement is that if you have a state which lies in DPST, then projecting it onto the CLDUI subspace doesn't hurt this membership property. So somehow one could formulate both of these statements in one compactor statement, but yeah, I like thinking about them in these two separate steps. Okay, and I initially wanted to give a bit of the flavor of the proof. So we are going to focus in on the first result here, but I guess I'm going to go over it a little quickly. So okay, we are given a CLDUI state, and we have an extended state satisfying the three properties of before. And now we want to argue that the projection onto CLDUIT still satisfies these three conditions. And for ease of notation, I call this rho tilde ABT. And okay, so we have three conditions to check. And two of them are easy, which are the linear conditions. So in essence, what happens in the partial trace is that, I mean, you're putting a bunch of entries to zero in this step, but you're only putting those things to zero which needed to sum up to zero anyways. They need to sum up to zero because the partial trace needs to evaluate to rho AB, which is CLDUI, which has a lot of zeros. So that's okay. Then the second condition, the PSD conditions, are the ones where I think the most work is required. But this, in essence, breaks down to the fact that the projector we've seen earlier with the integral representation commutes with the partial trace. So, oh, this is a typo then. This should be partial transposition, sorry. What I wanted to say is the projector commutes with the partial transposition. So you're asking whether this object is PSD, but then you can instead just push this inside the integration, and then you are hitting something which is PSD with unitaries from both sides. Everything stays PSD. The PSD clone is closed. This works out. And then the third condition is probably the easiest one to see, since whatever we are doing in the projection onto CLDUIT is symmetric in all copies of the B register. So this projection does not hurt the symmetry. Okay, so this is a rather rough overview of what the proof goes like. And okay, so maybe in the last 2 minutes I try to argue why this is a nice thing to have. So, okay, to summarize, what we've seen so far is you have a CLDUI state, you want to test membership in DPST, and we now know that you can restrict yourselves to DPS certificates which are of a specific sparsity pattern. And now what I want to argue is how can you exploit this sparsity pattern if you want to implement the underlying SDP. So for that we look at some quick more examples. So here's again the example for n equal 2 of the sparsity pattern of CLDUI. So we've seen this before, but I use this to introduce this notation here. So after permuting the rows and the column, you have a block diagonal matrix. And the biggest block is of size 2, and you have one of them, and you have 2 singletons. So this is what I mean with this notation. And here's the first picture of the sparsity pattern of an CLDUI 2 state. so of an extended state. And what one can see is a similar block diagonality occurs again. And it actually behaves as nicely as one can wish for. So the result is not only is the extended state block diagonal, it is also block diagonal under arbitrary partial transpositions. So if you want to run your SDP, you need to check whether all partial transpositions are PSD. And then with this block diagonalization, you can do this more efficiently. So here I have two tables of just showing some of the block sizes. So these are the block sizes for the CLDUI case. In this column, we have the different ambient dimensions. And then in the row, we have how far we extend the state. And then, for example, for n equal 3, t equal 2, you would need to run an SDP which has 3 blocks of size 5, 4 blocks of size 3, 9 blocks of size 2, and 18 singletons. And we can now compare this to what would the block sizes look like if you don't exploit any additional structure. And one can see that these numbers really are drastically lower than in the general case. So I like to focus on the bottom right of this table, where in the general case you have the biggest block is of size over 1,000, and this reduces to a block of size 35. So all of a sudden, in smaller n and t, you can even do things by hand, which was impossible beforehand. There's some subtleties with these numbers, but I think I'm already over time, so I end on this. Thank you very much.
Thank you. Questions? He's closer.
Thanks. Can you go back to the definition of the DPS?
Yes.
In particular, the extended state, I mean, you've written it, it seems to be like pure and separable already, like the way you write it down.
Yes.
Okay, but you want to check for generic state if it belongs to the class, right?
Yes, I think this is the point of confusion I mentioned earlier, but let's go through it slowly again. So the point is I'm giving a recipe here for something which is separable, and I'm arguing how, if something is separable, you can build the extended state. So in essence, what I'm arguing is this inclusion here.
Okay.
But, I mean, assume your state is not separable or you just don't know. You can still ask the question whether this bigger state exists satisfying these conditions. But you don't know how it was cooked up. It doesn't need to be cooked up like this.
Okay, perfect, thanks.
Thank you for the nice talk. So the DPS hierarchy is usually used when we have like a state and we want to test how close it is to being separable, right? And if we do the DPS hierarchy on like a CLDUI state, then probably are we somehow testing how close it is to a CLDUI separable state? Or is it still to all separables?
I mean, if you start with a CLDUI state and you're asking whether it's separable, then, I mean, it is already CLDUI.
Mm.
So the answer is yes, but not much is happening, right? You're starting with a CLDUI state and you're asking whether it's separable, then.
Do we understand the separable states which are CLDUI?
So what you can do is you have your separable decomposition, and then you can apply the group averaging onto the separable decomposition, and this will give you this will stay a separable decomposition. But it is not true that, for example, all the atoms need to be CLDUI. So only in the average, the resulting state needs to be CLDUI.
Okay, so there's like no easy way to like simplify the decomposition somehow if you know that a separable state is CLDUI?
Not that I think the answer is no.
Okay.
Yeah. I mean, and in particular, it breaks down to asking whether these matrix pairs are pairwise completely positive, which is this generalization of complete positivity, and I think membership there is also NP-hard.
Okay, okay.
More questions? Well, if not, let's thank our speaker again.